yeah, the next 20 minutes, I want to discuss a little bit more about post-quantum cryptography, and specifically looking at the standardization efforts that have been going on so far. So to recap, so there's this quantum threat that's explained in the previous talk, but maybe I want to give a little bit more background. So there's an algorithm called Shor's algorithm, which was designed in 1994. And what it does is it does a very specific task, namely it finds the period of a periodic function. And it turns out that, I would say it's an unfortunate coincidence, that the crypto systems that are in use today, basically RSA and ECC, can really be reformulated as a finding the period of a periodic function problem. Now, like I said here, it's really an unfortunate coincidence because there are other cryptographic schemes, even before ECC existed, that do not fall to Shor's algorithm. Also, as explained in the previous talk, so Shor's algorithm runs in polynomial time, so we really cannot save RSA and ECC, so we really have to look for replacements of these algorithms. Now, there is a second algorithm called Grover's algorithm, and it's also a quantum algorithm, and what it allows you to do is it allows you to speed up search. So if you have a set of n elements, normally if you want to look for one particular element, you would have to do exhaustive search, so you would have to visit all of these n elements. But using a quantum computer, you can actually speed this up into square root of n time. Yeah? So it doesn't go from an exponential time to a polynomial time as with Shor's algorithm, but it does actually speed up exhaustive search. Now, this also, at least in theory, influences the other types of cryptography that we're using, namely symmetric key cryptography. And in theory, we would actually need to double the key length or the output length of the hash functions. Yeah. But if you really look at this algorithm and you count the number of gates that you need and you count the effort that it would really take in practice, you see that, in fact, there is no big improvement of this quantum attack on symmetric key cryptography. And so the conclusion is that current schemes that we have, such as the advanced encryption standard and SHA-2 and SHA-3 as hash functions, actually they don't need to be replaced at all. So we can keep those. So the main thing we have to replace is the RSA and ECC. So I keep on losing my presentation window. I don't know why this happens.
For us, it's still visible, and we see your cursor as well.
Yes, but for me, it shows the screen of the. Okay, so I guess you can still see it, right?
Yeah.
Yeah. So yeah, to recap, we need to find replacements for RSA and ECC, and not for the other symmetric key crypto systems that we have, like AES and SHA. So NIST, which is the National Institute for Standardization of the US, also realized this and already quite some years ago. And in 2016, they actually made a call for proposals for new schemes to replace RSA and ECC. And the call consisted of two primitives, namely key exchange and also digital signature schemes. Yeah? So like explained in the previous talk, so key exchange is where two parties agree on a common key, but this is not sufficient. So in practice, we also need authentication. Yeah? So you have to know who you're talking with and if the messages that are being received are really authentic. So for this, we need digital signature schemes. And so NIST wanted to replace the ones we have or are being used today based on RSA and ECC. And so they made this call in 2016. And then it went through different rounds in the competition. So the first round started at the end of 2017, and there were 82 submissions for new schemes. Yeah. Already in the beginning, many schemes got rejected by NIST because they didn't actually satisfy the requirements, or they got broken in the first couple of months. After 2 years, the situation settled somewhat, and then 26 of these 82 schemes were chosen to proceed to the next round. And then finally, in 2020, we had the round 3, where NIST said, okay, these are 7 finalists that we are really looking at in detail, and then we have 8 alternate schemes that we can somehow use as a backup. And then 2 years or 3 years ago now, NIST finally announced 4 winners. So they took one key exchange scheme, which is called Kyber, and 3 signature schemes. And then they said, well, we still want to study some of these other alternatives more in detail. So we're going to have a 4th round where people can still cryptonize the schemes that we have in the alternates. And then furthermore, I will show you in a second. So the new signature schemes, they have quite larger signatures compared to the existing signature schemes. And then so NIST said, okay, we're going to have a new call specifically for signature schemes to complement the schemes we are already going to standardize. The call specified that the schemes should satisfy some security levels. And in practice, you will typically see level 1, 3, and 5 because they correspond to symmetric key cryptography, which is AES-128, AES-192, and AES-256. So here is an overview of the types of schemes that were submitted to the NIST competition. And also these numbers in the different rows, they just mean how many signature schemes or encryption schemes were submitted of a given type, and then how many survived the different rounds in the competition. So you can see that in the left column, we have the hard problems that these new schemes are based on. So the first one and the most popular one is called the lattice-based scheme. And these are cryptographic schemes based on hard problems in lattices. So a lattice is like a high-dimensional regular grid of points. And one of the hard problems there is to find, given a point, a random point in the space, given such a point, to find the closest lattice point. Then there are several schemes based on codes. So there the assumption is that a random linear code is hard to decode. Multivariate means it's hard to find a solution of a system of equations of multivariate equations. And then hash-based means you're just using a hash function to create a signature scheme. So as you can see, there aren't any encryption schemes or key exchanges based on hash functions. So we only have signature schemes. The advantage of these schemes is the security is very well understood because it completely reduces to the security of the underlying hash function. And then there are some more exotic schemes which are in the category other. So to have a more detailed look at some of these submissions, so this is what NIST ended up with in the final round, basically. So as you can see, most of the schemes are lattice-based, both signatures and chems. Then there was one hash-based scheme left in the final round, 3 code-based schemes, 2 multivariate-based schemes, and then 2, which I call more exotic schemes, Picnic and Psych. Now, out of these schemes, the ones in bold, so the Lithium, Falcon, Kyber, and Sphinx Plus, they have been chosen to be standardized. Yeah? And so currently, so last year, NIST finalized the standardization of the Lithium, Kyber, and Sphinx Plus. And the standard of Falcon is still ongoing because it's more complicated than the other signature schemes, Lithium or Sphinx Plus. So we submitted Saber, so this was our scheme. Unfortunately, it wasn't chosen as the standard. And then there are several other schemes, for instance, FrodoChem, that is also a lattice-based scheme. It has less structure than the Lithium or Falcon. And for instance, it's also being standardized by the German government and by the French government. And then currently in round 4, people are still looking at the code-based schemes, but the German government has already decided to standardize classic matrices. It's unclear if NIST will also do that, but the Germans have already done that. Now, during the final round, a lot of cryptanalysis was still being performed. And in fact, both of these multivariate schemes, so GEMS and Rainbow, both were broken in the final round. And also, so Psych, which is an isogeny-based scheme, was also broken in the final round. And really, it was a polynomial time attack, so it's not something that that can be saved. It was really a tremendous breakthrough. And both Rainbow and Psych were broken by researchers in COSIC, which is in our research group. So let us now look at the first standard, which is the NIST standard ML-Chem, which stands for Model Lattice Key Encapsulation Mechanism, or the other name is Kyber. So if you look, so if you compare it with, for instance, ECC, a couple of things you will see. So the negative point is that everything is bigger. Yeah? So the ciphertexts, for instance, are 12 times larger. The keys are even 25 times larger than ECC. Speed-wise, I would say it's comparable or even better than ECC. So when you're looking at speed, it's an improvement. When you're looking at size, it's actually quite a bit worse than when you compare to ECC. Similar picture for the digital signature schemes. So again, when you look at the numbers compared to, for instance, signature scheme based on ECC, you will see that, well, everything gets bigger, and that the hash-based schemes, so Sphinx Plus, are quite a bit slower for signing, but the other timings are comparable, I would say, to ECC, or even a little bit slower, but not too much. But again, looking at the signature sizes, things are quite a bit worse, right? So for instance, the Falcon signature size is 10 times larger than an ECC based signature size, and for the lithium, it's even worse. It's almost 40 times larger. So you might wonder why NIST has already standardized the lithium and not yet Falcon. And if you compare these two schemes, so what we know about them is that the security is fairly well understood, I would say. Both of them are efficient, but like I said, the main problem is that the keys and signatures are larger than pre-quantum, especially when compared to ECC. Now, when you compare these two schemes, then you can say that the lithium is kind of simpler than Falcon, because Falcon really uses double precision floating point arithmetic, and this has to be done in constant time. Yeah? And this is something which is quite new in cryptography, and that's why the standard is taking quite a bit longer to write, because NIST wants to be sure that the specification really takes this into account. Now, the advantage of Falcon over the lithium is that the signature size is like 4 times smaller. But at the moment, there is no finalized standard yet, and we expect it to be ready somewhere in the summer of 2025. So how will you continue? So there are different approaches on how to do this. So one approach is to actually use like a middle area, which is called the hybrid area, where you're going to combine both classical schemes with post-quantum schemes. Yeah? So for instance, you could have, if you want to sign a document, you could sign the document with both a classical scheme and a post-quantum scheme. So this is an AND approach where you use both of them, or you can also use an OR approach, maybe for backwards compatibility for a couple of years, where you say you can either use a classical scheme or you can use a post-quantum scheme. So this is just a solution for the next coming years, I would say. And then once everything is ready, so the standards are fully specified, products are available for the post-quantum schemes themselves, then the advice would really be to actually move fully to post-quantum solutions. So one of the main issues that will happen is that if you look at the PKI infrastructure, we will run into problems there because of the sizes. Yeah, so both the public key sizes as well as the signature sizes, because they have increased so much. Many of the products that are out there, they will break because they can't actually handle such big sizes. So you might wonder, well, by when do we actually have to upgrade to these new post-quantum cryptographic schemes? And so depending on who you ask, there are different answers. So NIST recently published a document that specifies that everything should be moved by 2035. Yeah? So here you can see that they still allow classical schemes based on RSA on ECC up to 2035, especially when you use them at the security level of 128 bits. But afterwards, it's really disallowed. Yeah? So by 2035, you should be fully moved to post-quantum cryptographic schemes. Now, NIST does allow, even after 2035, does allow the use of hybrid schemes. Yeah, but like I said, in the end, it's much easier when we would just fully move to post-quantum cryptographic solutions, because then, yeah, it's more efficient than using a hybrid scheme, and it's also simpler in the end not to use two different types of schemes just to do one operation. Now, if you ask the NSA, they actually have a slightly different answer. First of all, they only allow a very specific subset of the algorithms that I showed you before. So for instance, they don't allow Sphinx Plus, and they only allow Crystal Kyber and Crystal Dilithium. So they also don't consider Falcon because it's not standard yet. And so here you see that especially for software and firmware signing, they already say that the transition should be on its way. Yeah. And for this, you can use two other hash-based signature schemes, which are called LMS and XMSS, that were standardized before also by NIST and are not part of the NIST competition. The slight downside of these schemes is that they really are stateful, which means that you have to remember some state. And because of this, both NIST and NSA say you can only use these schemes when they are implemented in a hardware security module, because that can really keep the state. And one difference is also that, so the NSA doesn't actually allow for a hybrid mode. It just says you have to move to post-quantum crypto and don't actually allow for the combination of both schemes in the meantime. So here are the conclusions of the talk. So currently, NIST has already standardized 3, so has published 3 standards already, and is working on the 4th one, which is Falcon. Yeah. So a couple of years ago, it already published 2 standards for hash-based signature schemes, LMS and XMSS, but these are really for restricted use only. Yeah. For instance, the NSA specifies that these can only be used for code signing, and they should also be used in combination with the hardware security module. The process is still very much ongoing. So the round 4 is ongoing. The extra call for extra signature schemes is ongoing. So we can expect that several other schemes will be standardized in the coming years. And especially for the signature schemes, this will be interesting because hopefully, NIST will standardize signature schemes that have much smaller signature sizes compared to the ones we have now. So efficiency-wise, it's pretty okay, especially when you're looking at lattice-based schemes. So I would say it's comparable to ECC. It's even faster when you look at the CHEM, maybe a little bit slower when you look at signatures. But overall, efficiency is not going to be the big problem. So the big problem, like I said many times before, will be larger keys, ciphertext signatures, and many products that expect, let's say, a certain maximum size of a signature, they will not be able to handle much larger signatures. So they will really need to be updated and upgraded. I haven't said anything yet about implementation security, but this is another ongoing effort to actually create secure implementations of these standardized algorithms. So the reference implementations that you will find on the NIST website, they are all constant time implementations. But of course, this is not sufficient. So we would have to also look at other side channel attacks that are possible. And then because of the size problem, so upgrading the public key infrastructure, that will be a major challenge because like I said, many products will have a maximum limit on certain objects, and the signature sizes will now be bigger. And then finally, when should this all be done? So depending on who you ask, it should either be done by 2033 or by 2035. So to finalize, so if you want to read a little bit more, there is a very interesting book, which is called the PQC Migratie Handbook. It was written by the Dutch government. And it really gives you a very nice overview of the different schemes, both classically and post-quantum, and how you should actually go about migrating to these post-quantum solutions. And then the other references are just references to the standards of NIST and the remarks of the NSA on how the transition should occur. Okay, so that's the end of my talk.